This machine could be the forerunner of the family plane for weekend flyers. But have we enough sky for them? Already civil and military aircraft are flying in ever-increasing numbers. How is it that they don't collide with each other? And how do the pilots know where it's safe to fly or what altitude to keep? They follow aerial roadways mapped out by radio signals, and they even have junctions signposted by radio beacons called fan markers, which light indicators in the cockpits. Within a range of 150 miles or so, ministry staff can be in direct contact with the pilots. And if you've come a long way in a jet airliner, you won't have much fuel in reserve, so they'll get you down as quickly as possible. But what about the slower planes? Well, they stack them up at different altitudes and bring them down one at a time in between jet landings. As a passenger flying into London Airport, you would hardly realize that your plane was only one of the 600 or more to touch down here each day. They come from all over the world, yet the traffic moves with the regularity and ease of a taxi rank. You'd be arriving at one of the major crossroads of the world, and you'd be one of the 4 million passengers who pass through this terminal in a year. As your pilot signs off, others arrive and sign on, while their passengers arrive by the busload. Some may only be going as far as Paris, others perhaps all the way to the Far East. For a few, it may be their first flight. While the passengers relax in the luxurious main concourse, their planes are being made ready. Over 60 million gallons of fuel are used here each year, and behind the scenes in the workshops, every aspect of maintenance is carried out. Some of the people here work for the Air Registration Board, while others may have been apprentices at another ministry organization, the laboratories of the Aeronautical Inspection Directorate at Harefield. Although apprentices are trained, the main work is inspection, which covers a very large field, from checking gears to testing the strength of metal bars by literally tearing them in half. These laboratories contain some of the most precise and up-to-date scientific equipment. To detect a hidden flaw in a metal casting, they use a technique similar to the one hospitals use when looking for broken bones. They take a picture of the casting by means of X-ray photography. Or, if the subject is a difficult shape, film will be attached to it and the exposure made by one of the byproducts of atomic energy, radioisotopes, and the rays give an even exposure all round. There are also laboratories where the Electrical Inspection Directorate can check standards and make insulation tests on components. Here, the operator is protected behind a shatterproof glass screen while he builds up the voltage to a point where the electric current creates a discharge. In another section, there is apparatus designed to test and measure almost every conceivable type of electric lamp. The majority of the work is undertaken for the Air Ministry and the British aircraft industry, and these inspection directorates make certain that aircraft components ranging from motors to landing lights are as reliable and safe as possible. Only a few years ago, night flying was a risky business, and although the glittering lights from a city could tell a pilot where he was, he still had to find his airport by compass bearings. Today, ministry staff take over the responsibility, using the latest electronic equipment to guide him straight to the runway. The approach lighting at London Airport was designed by a ministry scientist and named after him. The culvert system, as it is called, is so reliable that it has now been adopted by the International Civil Aviation Organization for use on runways throughout the world. During the winter months, however, there is an unwelcome hazard in the London Airport area: fog, and unfortunately it's a regular visitor. The ministry developed Fido as a wartime fog disperser, but it was expensive to run. Today, radar plays a big part in helping the pilot to bring his plane down, for although he may descend into an almost invisible world, there are others who can see and help him. He is in direct contact with the men in the control tower, who guide him onto the glide path by literally talking him down, even telling him, for example, when to lower his undercarriage. But this system only works when there is enough visibility for the pilot to see the runway at the end of his descent. Otherwise, he could not make a safe landing. Obviously, radar is not the complete answer to blind landings. So the RAE at Bedford are developing equipment which will land an aircraft entirely by automatic means. With this system, an aeroplane can fly itself onto the runway. The plane is controlled from the ground by electronics, and the runway approach is wired in such a manner that signals are transmitted which operate all the flying controls. The system is so efficient that the pilot doesn't have to do a thing. He could sit back with his eyes closed while the blind landing equipment controls everything from flaps to throttles to bring the plane down safely and accurately to make a perfect three-point landing, thus eliminating one of the worst flying hazards. Today, flying is becoming as safe as houses, and the pilot's thumbs up means more than just an engine start. It means that the combined effort of the aeronautical world, from research to operation, is steadily solving every problem the pilot once had to face. But when you glide smoothly into the air in a modern jet-powered airliner, or gaze upwards as a flight of jet fighters thunder overhead, it requires some effort to bring your thoughts down to earth again to think about the invention and development of the gas turbine engine. A large research establishment was set up at Pystock to further the work of Sir Frank Whittle, the man responsible for the design and construction of Britain's first gas turbine engine. And this is one of the very first jets. All the facilities required for this research work, including the most up-to-date engine test houses, are installed at the National Gas Turbine Establishment. Although the theory of jet engine design was known to the world in the 1930s, development was held up until a new metal, pneumonic, came along. Here, modern metals are subjected to extremes of heat and cold to see if they will withstand the tremendous stresses encountered in high-speed running. It takes power to test engines. These generators develop something like 350,000 horsepower, enough for a small town. It is easier to test an engine on the ground than in the air, and in the test cells it's possible to simulate flying conditions and check and record the performance of every single part of an engine. To obtain the information, hundreds of instruments, wires and cables have to be fitted, and these are fed through into the soundproof control rooms where the scientists can monitor the test runs in safety and comfort, working to carefully arranged programs. However, the problem of analyzing all the data shown on the dials and gauges is a formidable one. But an electronic computer works out in seconds calculations that would take a man 20 or 30 hours to solve. When an engine has to be tested in the air, it is mounted beneath this flying laboratory. Should a failure occur, the pilot can use the regular engines to bring the plane home. Many of Britain's prototype gas turbines were tested in this way, and some of these engines are now fitted to world-famous aircraft. What goes up must come down, so the old saying goes, but here was a startling conception. A machine flying without propellers, wings or fuselage. A revolutionary development of the gas turbine engine. The planners moved quickly ahead, and the next step was to build a fixed-wing aircraft which would take off vertically and then fly away in the conventional manner. This is the prototype of the airliner of the future, a completely versatile airplane capable of carrying passengers or freight rapidly to regions which at present can only be reached by the slower-flying helicopters. Because it can land almost anywhere, it forecasts perhaps the disappearance of conventional airfield runways. Today, however, they are very much in vogue, and the jet uses up a lot of runway in a short time. For the aircraft designer, it's a race to the skies. But high-speed flying means new fuselage shapes. How do these designers know what shapes to adopt? Part of the answer lies in wind tunnel research. The tunnels are designed to run at different speeds, and in some the models are watched on closed-circuit television screens. They use a lot of models. Each one is built to the most exacting scale dimensions and is patiently made by hand. They can test a new shape in a wind tunnel. Or they can plan modifications to an existing aircraft and learn how much the performance of that plane will be affected. With the aid of instruments, they can find out almost everything about the flying capabilities of a new design. But there are research problems which cannot be solved in the wind tunnels, and in this case, ministry staff traveled to Canada, where the winter conditions were ideal for experiments in de-icing helicopter rotor blades. An artificial cloud was produced by forcing steam through nozzles on this grid, while the helicopter was flown in the cloud until the moisture had frozen hard on the blades. It was a risky business for the pilot, flying almost blind as close as that to the grid tower. However, the tests proved worthwhile and some satisfactory de-icing systems were evolved.